have infinite more steps to go. 25 actions, I still have infinitely more steps to go. So saying saying that value function depends on horizon makes no sense because the horizon is always infinity. So there should really be a single value function for each state. That is a huge improvement now. Instead of the value function being dependent on both the state and the number of steps to live, number of steps to live is always infinity. Do you see what I'm saying? Number of steps to live is always infinity. And so essentially there should only be one value function, otherwise it won't make any sense. So just basically I have to compute V star S and then I have to compute pi star S. Now how would I compute V star S? Essentially V star S, of course I can just say this, that there are only finite number of policies right now. In fact, I told you also that if there is a single value function with respect to the amount of steps left, because it's always infinite number of steps left, policy is also not going to be independent of the number of steps left because it's always infinite number of steps. Which actually means that the number of policies are only a power s. Huge victory instead of a power s times h. Okay, and then the optimal value function is nothing but the value function corresponding to the optimal policy. That's kind of a crazy recursive definition, but that's what we really know. And the way you can compute the optimal function, the general idea is to essentially do the finite horizon. You keep doing the finite horizon backup. Okay, so if I kept doing finite horizon backup, this, etc. And the only difference is each time when I'm taking the value, just 1 second. So when I'm taking the value that's coming max here, I multiply it by a gamma before adding it to the R. That's it. That will ensure that I am discounting by gamma what happens in the next step. And whatever I did here already discounted what happens before that. If I were to do this, and if there should be a single value function, it stands to reason, of course, standing to reason is not how math is done, but it stands to reason that if I keep backing up, at some point of time, between V59 and V60, there is no difference. The value function converges. That's exactly what value iteration is. You run the finite horizon value iteration until the value function at kth iteration and the k plus 1th iteration are too close. In fact, we want to say they're equal, but we are talking about real numbers. Real numbers never become equal in computers with all the floating point errors and so on. So you basically take the difference between two value functions. Now, what is the difference between two value functions? You take the maximum difference between the value function in any single dimension. Value function is a s-dimensional function. There are s number of states over which you are giving the value. For each corresponding states, you take the difference. Take the max of those differences. That will tell you how far this is from this value function. When that difference is less than some epsilon that you set to yourself, you stop going back. That's it. What?
The last part that you said.
So what I'm saying is that basically if you have value functions, let's say this is V2 and V3, right? So now between V2 and V3, if nothing changed, is one way of talking about if the values here is the same as values here, I'm done. Equivalently, since they never will be exactly equal, I can take the difference between these two values, these two values, these two values, take the max, and say the max difference is bounded by epsilon. And I stop there. This is, as far as plug and check goes, this is all what you have to do. It's the Bozo mathematician's problem to prove that this will actually happen. Do you understand what I'm saying? I mean, I'm just kind of waving hands and saying it will happen, it will happen. And then, in fact, if you put gamma to be, if you put gamma to be less than 1, then essentially you can prove that the value function has a property called contraction property. Anytime you do the Bellman backup, the value function difference between two iterations is going to be strictly reducing. That's called the contraction property of the Bellman Bellman update. Let's see if I have. Okay, so I'll get back to the contraction property in a minute, but let me just say what I said in formulas, right? So V star of S, if there exists a V star of S, okay, it must have the following property. V star of S must be equal to R of S times beta times max over all possible A's of this expression of V star of S dash. Notice the difference between this and the previous expressions, but this used to be K and K minus 1. There is no difference between K and K minus 1 in infinities. Those of you who remember anything about your Markov chains, and when you try to compute steady state probabilities in Markov chains, this is what you wind up doing. You will essentially assume that if there were to be a steady state distribution, it should have satisfied the following equation. And then you find the steady state probabilities that satisfy the following equation. And if you remember a little bit more about Markov chains, you will remember that oftentimes, numerically, the way to compute the steady state probabilities, I mean, actually, if it's small enough, you can just solve those equations. Okay, actually, you can't easily solve it in this particular case because there are maxes. Okay, but in, either you can try to solve or you can try to use it as an update equation and keep doing it until between two iterations the probabilities don't change, in the case of Markov chain. In the case of MDPs, you keep doing it until between two iterations the value function doesn't change. At which point you say that is the optimal value function. Then you say, why did I need an optimal value function? I wanted an optimal policy. Then I'll say, you can convert an optimal value function into optimal policy in the same old way. Because you have, let's say, two actions I can do. Action 1 takes me with 0.7 probability to S1 and 0.3 to S2. And the other one takes me with 0.9 to S5 and 0.1 to S6. Then basically I do the calculation. 0.7 times V star, S5, etc., and then basically see whichever is the bigger value. And I pick that action. Okay? The same thing that we did in the finite horizon case. Except in the finite horizon case, you would always think of Vk and Vk minus 1. Here it's all just V star. Because the number of steps left is always the same. It's infinite. Okay? So now this is basically the equation. This is the equation that defines the value function for infinite horizon MDPs. You can directly solve this equation, but because there's a max, there is no closed form way of solving this equation. So instead, you just do the finite horizon Markov decision process value iteration, which essentially uses this equation as if it is an update rule, starting with the original estimate for V star to be just R of S, and then just keep doing it until between two iterations V values don't change. So then you come to the solution for this in an iterative fashion rather than in a closed form fashion. Now, one interesting question is, if I actually am trying to if I've given a policy, a single policy, and I'm trying to just compute the value for that single policy, then there won't be a max here. It will just be T S pi as S dash. As crazy as it looks, that would be a system of linear equations. We can solve linear equations in sleep. You may have forgotten, but you can just do matrix inversions and be done with it. So policy evaluation, that means converting a single policy into value, will not have this max sitting there. So it's a linear type, it's a polynomial type process because it's just solving linear equations. Computing the optimal policy involves a max, so you have to do this iterative process. Right? Okay? Now the reason why it works, I'm just going to quickly say that I said so. Basically, that you are essentially doing, so the difference between running finite horizon in the actual finite horizon case and in the infinite horizon case is that in the actual finite horizon case, iteration is equal to the number of steps left. In the infinite horizon case, iteration is just an iteration. It's just a computational artifact. It has no connection to reality. All you care about is the final value. function, which doesn't change between k and k plus 1. Okay? So now the question of course is, why do we believe that the value functions will slowly converge? That means between two steps they won't change enough at some point of time. And for that it turns out that there is a property that Bellman backup has called contraction property, which you can convince yourself of. I'm not going to do it here. That will show that when you do a Bellman backup on an entire value function, the difference between the value function before and after the Bellman backup would always be reducing. And if the difference is reducing at some point of time, it will go below epsilon, whichever epsilon you take. So that's your fixed point theorem. And there are some pictures here, but I'm not expecting you to understand this. This is more graduate level stuff as to why MDP is actually, why this is guaranteed to converge. As far as you are concerned, you can imagine that you're doing finite horizon enough number of times until the values between two iterations don't change, at which point you say you converged. Okay? And then you can convert it to policy. Okay, now how to act? If I give you the optimal value function, you can convert it to the optimal policy. Right? How do I do that? If I'm in state S, okay, if I'm in state S, I basically do the greedy action using just the value function. Okay, what I'll do is, basically, if I'm in state S, I can do any action A. For each action A, I see what is the maximum, what is the value I get, take the maximum. And the action that gives me the maximum is the action I'm supposed to do. Now, doing greedy thing when the value function is actually the reward function is not guaranteed to be optimal. Because I told you rewards are not necessarily proportional to value. But if you have computed the optimal value function, the greedy policy with respect to the optimal value function is also optimal policy. Okay? Once again, if you come to this from the finite horizon case, it's not surprising to some extent, because it should make sense. If there is to be a solution, it better reach a fixed point as you go forward. And at that point, you are essentially converting the value into policy, the same way you did for the finite horizon case. It's just that you only have value is independent of the number of steps to live. Yes?
So in other words, the greedy policy works best when you have the proper reward shaping?
This will work always. This will always work. Okay? The difference basically is, imagine if, as I said, essentially, if your reward function is actually set to be proportional to the value function, then even an agent which just does greedy thing is in effect doing optimal thing. Do you understand what I'm saying? Normally rewards are not proportional to the value. So you have to first convert it to the value function and then do the greedy on value, not greedy on reward. But if the rewards are made to be proportional to the value, then doing greedy with respect to reward is the same as doing greedy with respect to value, optimal value.
Okay.
That's the reward shape. Okay?
Yes.
Okay? That's about acting. We don't need this. There are different ways you can actually improve value iteration, but imagine that the simplest thing I want you to understand is you're doing, this is what's called synchronized sweeping. You do finite horizon value iteration, first we start from V0, do V1, V2, V3, V4, V5, until between two iterations, Vk and Vk plus 1, the value hasn't changed enough. And then you say that's the value function. The only difference between doing that and computing the finite horizon value function of a k horizon MDP is, after completing this, you will keep all the values, the Vk, Vk minus 1, Vk minus 2, all the way to V0 in the case of finite horizon. In the case of infinite horizon, the last value function is the only thing that you care. Because you always have an infinite number of steps to live. Okay, so to some extent actually it's an easier life. And the question of course is, we got here by playing this trick of ensuring that summation of infinite number of rewards properly discounted will always be finite. And you can think of this as just a mathematical trick I did to make sure that I can somehow write an algorithm Or you can also say that actually makes sense. People do discount future with respect to current rewards. Whether they do it exponentially or not remains to be seen, but it's intuitively a reasonable thing to discount rewards of future with respect to the current. And in fact, you can say your discount factor tells me something about how stable you think your world is. If you think your world is not going to change much, you'll have a very high discount factor. That means close to 1. If you think your world is going to end tomorrow, you'll have a low discount factor. Okay? There is a beautiful value iteration demo that I wanted to show you, but unfortunately it was written on the old Java and it's not running on any of them. So you may play with this thing. It actually shows you how the value function changes as you do this on a maze-like structure. Okay, and it gives you interesting, interesting insights. And one of the things that you will find, for example, is as the value iteration, as the iterations change, you will start seeing that the values of the functions first might reduce and then start increase and then stabilize. Okay, and that's because sort of the states realize that I have one of the things that the value iteration does in essence is I might originally be thinking I have this terminal state that I can get to, this other terminal state I can get to, and these are the only things I have, and so which one is better? Somebody much farther away from terminal states looks around and sees only rewards, and they can't differentiate between one action and the other action. But as you compute the values, iteration after iteration, everybody's value function becomes more and more close to its optimal value function. So the message comes to you that even though I have this state next to me, which is a very low reward bearing state, is actually a pretty high value state. So if I just do an action of getting into that state, then it will tell me how to go from there onwards. And this you can see playing out in this demo, and it will improve your insights, intuitions about value iteration. The last thing I want to talk about is that in the case of infinite horizon Markov-Adation processes, you can directly search in the space of policies instead of in the space of value functions. Okay, so here is the basic idea. I guess a policy. Okay, I guess a policy, then convert it into a value function. Because if I give you a policy, you can convert it into a value function by just doing this, linear equation solution. Right? Okay. Now, when you convert it to the value function, you now convert it back into policy. That makes you think this is obviously the end of the class. Rob is doing circular reasoning, and obviously I'm not going to go anywhere. The difference is the first one. So basically, when you started from a policy, remember, first of all, you realize there are how many policies? Finite number. How many value functions? Infinite number of value functions. Okay, so multiple policies may have the same, the sequence that I'm saying is you start with an arbitrary policy, compute its value, then compute the greedy policy for this value, and say that's my next policy, convert that to value function, compute the greedy policy for that again, and keep doing this until the value function doesn't change, and the policy doesn't change. Policy doesn't change means at no state is the action changing. Okay, so in particular, this is the picture. Okay, I have a loop. I start by guessing any random policy pi, okay, and then go through this loop. Evaluate the value for that policy pi. And then for each state S, set the new policy to be the greedy policy with respect to this computed value function. Because the thing is, when you just randomly set a policy, it can be inconsistent. It can be inconsistent. You're saying this guy is rich because he can go to the rich state, but I am poor. How can you be poor if you have a rich neighbor? In real world, you can be, right? But in MDP world, if you have an action of getting into the rich guy state, you too are rich. When you just randomly set each action's policy arbitrarily, you can be inconsistent locally. When you compute the value and take the greedy, it becomes consistent. Now you have a new policy. Then you compute the value function corresponding to that policy. Keep doing this until between two iterations the policy doesn't change. Policy doesn't change means there is no state where the action is changing between previous iteration and the next iteration. Now the nice thing about this is the policy iteration essentially is going to be in some sense searching in the space of policies, and there are only finite number of policies. So it's not surprising that actually the policy iteration can sometimes be faster than value iteration. Okay? One other thing. Here I said evaluate VPy, and I said you can evaluate VPy by just solving a bunch of linear equations. Some of you think, I don't want to solve linear equations. I forgot how to do matrix inversion. Turns out you can just run a bunch of backups without the max until the value function doesn't change between two iterations. And that will be the value of the policy. Did you understand what I'm saying? Normal value iteration does the max operation. Normal value function does normal value function does the max as the update. If I have a policy, then I know what is the pi SA. There is no max. It's set of linear equations. But you can solve these linear equations also in an iterative fashion. Instead of doing the max operation, you just do the, just basically every time you say, this is what the policy is saying, this is the action the policy is saying, and then I use that to compute the next iteration of the value of this policy. And after some number of iterations, the value of this policy will stabilize. That would be the true value of this policy. You will got into it by solving the linear equations too. Okay? So that's called the policy iteration, and it's cute because the number of policies are much fewer. I won't go through this. And actually, in the last 5 minutes, I want to go over this, not go this either. This also I won't go. I want to connect this back to game tree search, so that you have some reason why MDPs and game trees were done right after each other. Okay. So a very quick recap: we did MDPs, we did finite horizon and infinite horizon. For both, we computed exact optimal policies. Now, for the games, we never computed exact gameplay. We realized that you can compute exact gameplay if you go all the way down to the nodes where each leaf node is a known win or a known loss. Or basically, it's a terminating game. And then you can do min-max backup. Okay? You can do that in MDPs too. You can expand MDP tree. So suppose I have an MDP like this. Remember this one? In the very beginning of MDPs, we looked at this. I can imagine MDP as a game against nature. So I'm in this state. I can go this way, this way, this way, or this way. If I go this way, nature, so then I can either get into this or this or this. Those are the outcomes. That's like another player decides which of these I'll get into. I don't have control over which one I'll get into. The difference is, in the game tree, I don't know what my opponent will do at all. In a game against nature, I have probabilistic understanding of what the nature would do. You're saying with 80% of the cases I will get to this state, and 10% of the cases I'll get to this state, 10% of the cases I'll get to this state. Okay? Now, if I tell you what is the value of these nodes, you can back up the values. I can compute the value of this node and then see whichever is the action that is giving that value, that's the action I'm supposed to do. So in fact, while MDPs, we acted as if we have to compute the entire policy before you start to act. I also told you that sometimes life is too short to compute the optimal policy. What you want to do is, rather than just randomly pick one of the actions I can do, at least look a few steps ahead. Okay, and then see, now that I'm in this particular state, if I think 2 or 3 steps ahead, which action looks good and do that action. And then see where I get to. Then again do this. This converts my reasoning into an online decision making, where essentially I can just do the decision making, do the execution, do the decision making, do the execution. That's what we needed in games, because in games don't stop while you're thinking. It looked as if MDPs can stop while you're thinking, but MDPs also don't stop while you're thinking. We just convince you, basically we just looked at computing the exact policy, exact value, but really it's too hard to do that. So one way is you start from where you are, expand the tree in terms of the actions and the possible outcomes those actions can have, and stop at some point of time, and that point of time give a heuristic value for each of these leaf nodes. In the game trees we used an evaluation function, remember? Okay, here you can just, and I already told you V is like a heuristic. So if I can give a reasonable heuristic value for each of these states, and if I back it up using this expectation maximization, then in essence I am computing optimal way of doing action based on the state I am in. And this would be game against the nature. And the difference is, in the game against the nature, you have these probabilities and you think essentially that nature is following these probabilities. In a game against an opponent, you assume the opponent will cause you maximum damage. Okay, and if you're an eternal optimist, then you assume that only good things will happen to you. Okay, so that's basically, there is an idea called, remember the whole idea of MDP solution is dynamic programming, right? And so you can talk about something called real-time dynamic programming, which essentially expands the tree to k levels, gives a heuristic value for the leaf nodes, and backs it up level by level. At each level, when there is a probabilistic outcome, you take an expectation, and when the agent has to pick between actions, it picks the action that leads it to the maximal value state. Instead of min and max, it will be expect, max, expect, max. That's what MDPs are doing. Okay, so in fact, game tree ideas can be used in MDPs, or in other words, you could have said in game trees too, I would just compute the optimal strategy and will start playing. And then you don't have to play with anybody, because nobody will wait around for you. So games are interesting because they'll force you to do online decision making. Normal general idea would be for A-star search as well as MDPs is, first let me think, figure out the policy, then I'll execute. You don't have that much time. So you just basically go some number of levels deep. The deeper you go, the better your quality of your decision is. Again, the same idea. Okay? So if you have deterministic actions, real-time dynamic programming becomes something called real-time A-star search. That completes the circle. Why should it be the case that A-star search agents must figure out the full path and then start executing them? They too can have less amount of time. Well, A-star is nothing but MDP. It's just that the actions have a single outcome. It does never have expectation. So you do the same exact thing for A-star. Let me just go there. Something like this, which is a deterministic problem. I have a situation like this where it's just each time when I do an action, I get just one outcome. And I get to some, leaf nodes. At the leaf nodes, I apply the heuristic. Whatever the heuristic you picked. And then you backed up. That would be called real-time A-star search. You will be forced to play real-time A-star search if I tell you, you have to make a move, in every few seconds. Or the total amount of time I give you for thinking as well as doing is only this much. And so if your friend tries to compute the optimal path using A-star search, the clock goes off because they haven't yet found the optimal path, so they haven't even made a single move. Do you see what I'm saying? So, in essence, everything is connected. And it does look like that by the end of this class, as if everything is connected because you're all confused. but they are connected in a deeper sense. Okay, MDPs can be done. Game trees force you to not ignore the online aspect, because you cannot just say I will take infinite amount of time to decide what my next move is. So they'll force you. Game trees, you started game trees by thinking about limited depth, min max. For MDPs, for 2 full classes, I kept talking about how to compute optimal policies, optimal value functions. And only in the end I said, you will never have any hope of computing optimal policies and value functions. More likely you will do real-time dynamic programming. And real-time dynamic programming can be thought of as this general idea, one side of which is min-max backup, other side of which is RTA star, which is real-time A star search, in the middle sit MDPs. Okay, I'll stop here. Next time we'll change the topics, but this is the end of MDP.